Have you ever stopped and wondered how we build our world? You know, the towering skyscrapers, the super fast computers in our pockets. Well, the secret isn't just big ideas. It's about mastering the tiniest building blocks of the universe. It's about understanding and then shaping matter itself. Welcome to the world of material science and engineering. And this image? This pretty much captures the entire field in one shot. Over on the left, you've got the blueprint, right? That's the atomic lattice. It's where the fundamental properties of any material are born. And on the right, you see the final product, a massive, high-performance wind turbine blade. The journey from that atomic blueprint to a real-world application, well, that's the magic we're talking about.
You know, you can actually define our entire human history by the materials we've mastered. The Stone Age gave us our first real tools. Then came the Bronze Age, which gave us stronger weapons, better art. The Iron Age literally built empires. Every single leap forward was unlocked by a new material. And today, we're living in this Silicon Age, where we're engineering our world atom by atom to create all the tech that defines our lives.
Okay, so how do we actually do it? What are the rules to this game? That's what this playbook is all about. These are the core principles that every single materials architect has to master if they want to build a future. This field really has two sides of the same coin, and it's important to get this. On one side, you've got materials science. Think of this as the why. Scientists are digging deep using tools like electron microscopes to figure out the fundamental link between how a material is built inside, its structure, and what it can do, its properties. Then, on the other side, you have materials engineering. That's the how. This is where we take all that fundamental knowledge and apply it to design and build real things, like the incredibly complex battery and chassis of an electric car.
Now, at the very heart of this entire field is a super powerful idea we call PSPP. Seriously, this is the central logic. It starts with processing. That's how we make the material. This directly controls its internal structure on a microscopic level. That structure, in turn, decides its properties, things like its strength or how well it conducts electricity. And ultimately, those properties determine its final performance out in the real world. For instance, if you rapidly cool steel, a process called quenching, you create a hard, brittle structure. But if you cool that same steel slowly, you get a softer, more flexible one. Same atoms, totally different processing, and completely different performance.
So here's the absolute key takeaway. If you can control every step of this chain, from the processing all the way to the properties, you can design a material that gives you the exact performance you need for a specific job. This is the core logic of our entire discipline. It's everything.
All right, but here's the thing. In the real world, choosing a material is never that simple. There's almost never a single best material for anything. Instead, engineers are always facing this dilemma, this constant game of trade-offs to find the optimal solution for a specific job.
This chart shows that dilemma perfectly. So on the vertical axis, you've got stiffness. On the horizontal, you have density, or basically weight. Take a look at the metals up in the top right. They are incredibly stiff, which is great, but they're also super heavy. Now look down at the polymers in the bottom left. They're lightweight, fantastic, but you have to sacrifice a lot of that stiffness. See, you can't have it all. This is the core challenge. Every material choice is a compromise, a trade-off, finding the right balance for the job. Okay, I know this might still feel a little abstract. So how does this complex balancing act actually play out in a product you probably use every single day?
Let's talk about the simple beverage can. The problem is the same. Hold a liquid, often under pressure. But look at the different solutions. Aluminum is awesome because it's lightweight and recyclable, but making it from scratch is incredibly energy intensive. Glass is great because it's inert. It doesn't affect the taste, but it's heavy and, well, it shatters. And then there's plastic, which is cheap and flexible, but it comes with huge environmental questions. So one goal, 3 materials, and each one represents a completely different set of engineering trade-offs.
So, to solve these kinds of problems, engineers basically have a palette of 4 main types of materials to work with. You've got metals, which give us strength and conductivity. They're the backbone of our power grids. Then you have ceramics, which offer amazing resistance to heat, making them crucial for things like next-gen EV batteries. Polymers are all about being lightweight and flexible, perfect for things like battery casings. And finally, composites, like the carbon fiber in those massive wind turbine blades, let us mix and match to get the best properties of different materials all in one.
Now, what's really cool is that this field is always evolving. And a lot of that evolution comes from 2 places: learning from our biggest mistakes and pushing the absolute boundaries of how we build things.
Let's look at the famous case of the Liberty ships during World War II. These ships were literally breaking in half out in the cold waters of the North Atlantic. Why? It was a catastrophic materials failure. The specific steel alloy they used had a nasty secret. It went through something called a ductile to brittle transition at low temperatures. So a material that was tough and strong in the shipyard became as fragile as glass out in the freezing ocean. That, plus some design flaws, like sharp corners that focused all the stress, was a recipe for disaster.
But that disaster taught us one of the most important lessons in all of engineering. Failure is the blueprint for better design. By studying exactly why those ships failed, we developed the entire field of modern fracture mechanics, which makes everything we build today, from planes to bridges, infinitely safer.
Now let's jump from large-scale failure to the absolute cutting edge of creation, the nano realm. On the left, you see the traditional top-down method. We basically take a big chunk of material and we carve or etch away at it until we get something small. But the real revolution is on the right, the bottom-up approach. Here, instead of carving, we're actually learning to build structures atom by atom, designing materials that can literally self-assemble into the exact shapes we want. This unlocks completely new properties that are just impossible to get any other way.
And this incredible new level of control is leading to some amazing advanced materials. I mean, we've got semiconductors, which are the brains inside all of our electronics and solar panels. We've got biomaterials designed to work perfectly inside the human body for things like implants. And we even have smart materials that can sense a change in their environment, like heat or pressure, and actually respond all on their own.
So, all of this brings us to the future. And more importantly, to the role that you, as the next generation of materials architects, are going to play in solving some of the biggest challenges the world has ever faced. And believe me, the challenges are huge. In energy, we desperately need better batteries and more efficient solar cells. For transportation, we need materials that are stronger but way lighter. For sustainability, we have to design plastics that are fully recyclable. And with our planet's limited resources, we need to find smart alternatives for rare and critical metals. You have to realize, every single one of these massive global challenges is, at its core, a materials science problem just waiting for a solution. So how are you going to solve these problems? By mastering one final critical concept, the feedback loop. Remember that PSP chain we talked about? Well, it's not just a one-way street. The actual performance of a material gives you crucial feedback. And that feedback lets you go all the way back to the beginning to tweak the processing, which changes the structure, which improves the properties. It's not a line, it's a continuous, powerful cycle of innovation and improvement.
And this, right here, is the ultimate takeaway. Mastering this loop is what gives you the power to precisely engineer the brand new materials we're going to need. It is the tool that you will use to meet the incredible technological, energy, and societal challenges that are coming our way.
The game has changed. It's no longer about just finding the right material on a shelf. It's about designing the exact material we need, from the atoms up. So the only real question left is, what material will you create to define our future?